How many of you are currently Netflix subscribers? Ooh, nice. How many of you actually use some kind of stream processing or event processing system in production? Nice. Okay, a lot of you guys. So I think let's get started. So just like any specific domain of problems that you're trying to solve, it acquires a certain terminology. There are certain patterns evolve over time. And the field of dealing with unbounded data processing is no different. So I'll go over some of the terminology, some of the concepts, how to deal with unbounded data processing. We'll look into existing stream engines. I'll cover 3. There are a lot more out there. And then we'll look at what we are doing at Netflix to handle these challenges at scale. So we'll start with getting to know our terminology. The first thing that we observe is how we describe the data, right? Today, we talk about streaming to mean a couple different things. We mean it's an infinite stream of events that are flowing into our system, and we also use it to refer to like an execution engine. So for example, you may say, I'm using streaming data or I'm doing streaming analytics, but at the same time, you might be referring to the kind of processing it's doing underneath the hood. Maybe Storm, maybe Flink, or you may be referring to batching to mean Spark. And the same thing with batch. You may be using it to mean a couple different things. You may be using it to mean a bounded set of data or events that are flowing into your system, or you may use it to mean the type of execution engine that's handling that data. So let's be precise about our terminology because it's going to make a difference of how we address certain things when we're talking about it. Let's use unbounded to mean an infinite set of data or events that are flowing through, and bounded to just mean the finite set. And we can use streaming and batching to mean whether at the core the engine is streaming or a batching engine. So we could say a streaming execution engine can handle either bounded data or it can handle unbounded data set. And likewise for batching. Right? So for example, with Hadoop, you can actually not only do real-time data by just segmenting it, and it's been done for quite a long period of time. You just segment into an hourly boundary, and then you kind of deal with 1 hour chunk of data at a time. And you could do the same thing with streaming. You could take a finite set of data, like a file, and make it look like a stream and process it that way. So whether it's streaming or batch, both those engines can handle bound or unbounded data once we have the clear terminology. So you may ask, how do I choose a certain processing engine? So there are 3 factors you need to consider when you want to choose one. You have to choose between the trade-offs of latency, cost, and what kind of accuracy you're looking out of your system. And you should choose an engine that lets you make these trade-offs, but does not make it for you. So you need to have the option open for a use case so you can choose between these 3 and make a wise decision. The next important aspect is processing semantics of your events that are flowing through. Do you care that you want to process every single event that's flowing through a system? If you're doing metrics and you just want a ballpark understanding of what's happening, maybe a 0.1% or 1% of drop really doesn't matter. But if you're doing like billing and you're doing ad clicks and you want to charge back to your customers, the accuracy really comes into picture, and you don't mind paying the extra cost to get that accuracy. And we have the notion of exactly one semantics. Quite often this is misunderstood as exactly one's delivery, which is very different and very impossible to achieve practically if you think about it. So what we mean by that is, let's take a simple example. Let's say you want to add 3 numbers together. You add the first 2 numbers and your system crashes. And when you recover back again, you don't want to add the first 2 numbers again. So for example, if you're adding 2 plus 2 plus 2, When you come back up from a failure, you want the answer to be 6, not 8. Right? So if you do at least one semantics, you could get 8. If you do at most once, you could get 4. But if you do exactly once every single time, you should get 6, provided your source is repeatable and you're able to replay from it. So when it comes to accurately processing your batch data, it's relatively easy because you know the data set. The data set's not changing. And all you're doing is wasting a little bit of time because you're reprocessing it. Let's say it took 4 hours to process it. You have to reprocess it again. You take that extra amount of time. But when it comes to an unbounded data source, things are a little different. It's because your data is moving forward in time and you don't have an infinite buffer to hold it forever, you want certain consistent guarantees between failures. So you cannot start over a 12-hour job all over again and start from beginning. And the reason you may be doing the real-time processing is because you want that result early enough and not have to wait for it if it crashes. So you need a way to capture consistent state so that when it fails, you can resume from a good checkpoint. And the other thing you need is, if you want to do some kind of aggregations and groupings, you have to group your unlimited or unbounded data into smaller chunks. Right? There's no way around it. So you need good tools to reason about how do you group that, how do you deal with late data, how do you deal with errors in the system. So there's 2 really important concepts when it comes to unbounded data stream processing. The notion of time associated with event is really important as well. Broadly, you can think about it as 3 different times associated with an event. Event time is when the event is actually created and a timestamp that's associated with it. Ingestion time is relative to your stream processing engine. When it enters into the system, your system assigns a timestamp to it so that you know what time you actually ingested the event into it. And that ingestion time kind of remains constant throughout your processing. And the last one is processing time. That's the time when your computation operator or your engine actually sees that. So if you have a digraph of operations that you've connected together, each one will see it at a different time because everybody is not getting it at the exact same time. So let's look at the simple example to better understand those 3 concepts. So you have some kind of an IoT sensor that's emitting events, and you're capturing those events and assigning timestamps to it. So that's your event time. And it makes its way through maybe a queue or a messaging buffer like Kafka, and it enters into your processing system, and there's an ingestion time assigned with it. There are different use cases for it. So for example, you may just worry about, I just want to know how many requests per second I'm getting into my processing engine through my job graph, right? So an ingestion time is a good way to know that. Versus you want to know, what's happening on the sensor in the last 5 minutes, how many sensors did it emit or how many events did it emit. Then you want to go by the event time, otherwise your counts will be inaccurate. So if there are 10 events that were being generated in a 5-minute time span, but it took 8 minutes to deliver because of network issues or delay, then if you just say, in this 5 minutes, what did I get? You'll get a wrong answer because you missed the other events that came late. So if you do it by event time, then you get accurate results. Windowing. We talked about being able to group and make your unbounded data set bounded so you can do operations on it. And usually you don't need it if you're just operating on an element by element basis. So for example, let's say all you're doing is filtering and you're not doing anything else, then you really don't need windowing because you don't need a group of things to work with. But if you do want to do a group of things, like aggregation, or you want to group by, or you want to count some sum or average, then you need to bound your unlimited stream. Otherwise, you'll be buffering that data set forever, and you'll run out of resources to do any meaningful computation on it. So there are kind of 2 broad classification of windows. One is aligned and unaligned. With aligned windows, what we are saying is if you take a view into your unbounded stream, then everything in that unbounded stream belongs to your window. And you can have multiple windows into that view. With Unaligned, you're picking and choosing out of it. So like tumbling windows, sliding windows would be aligned because you're taking fixed chunks of your data, and everything that's in that chunk, you're using it for processing. Versus something like session windowing, you're picking and choosing which events fall into a certain window. So let's look at an example. So in this use case, we have an unlimited stream of events flowing through. We have some that come late in time, some arrive right in time. So we have an event that's occurring between 12 and 1 p.m., and the event time actually was between 11 and 12. And for the second one, it was between 12 and 1 p.m. So we see here that the event that we picked out into that window, and all of the events that fall into 11 and 12 will fall into that window, right? Versus if you look at something like, sorry, let me go back to the sliding one first. So we had the tumbling window where we have clear boundaries between the two windows, and there's no overlap. That means an element is not included in two windows at the same time that overlap. And if you have a gap between the windows, so for example, here these are 1 hour windows, and let's say the second window started at 11:05 instead of 11. Now you have a 5-minute gap there, and that's called hopping windows. So you can sometimes use it for sampling your data set, and when you don't want to process the whole stream. The next is overlapping, like sliding windows. So for example, you can say, every minute give me a count of the requests that are coming into my system, right? So you kind of, every minute you're looking at the events, and you may recount the events that fall across the boundaries. This is the example of unaligned windows, the session windows. As you can see, between the first 10 to 11 o'clock, the events that are in our input stream are actually being grouped into multiple session windows. So it's not symmetric, it's not aligned with the input. So that's why it's called unaligned windows. And you'll hear this in different literature, so it's kind of good to keep in mind when you hear these terms. So let's look at triggers. Now you've grouped your unbounded data set. When do you figure out you want to compute the results on it, right? We just grouped it right now. So triggers help you determine that, when exactly you want to compute results out of it. So it could be before you decide that my window is complete. So for example, if your window is an hour long, you don't want to wait for that whole hour before you get the results. You want to get a quick peek into it so that for operations, you can make sure everything's fine. So you could say every 5 minutes, whatever you have, just compute the results and show me so I can see progress that's happening. And so that's kind of before window. And then you can say when it's the hour boundary, give me results or emit the results. Or you could say do it later. So for example, you could get an event at 12:05, and you've already computed your window for 11 to 12, and you get one more extra event. You can roll that back into your sum later on. So the triggers kind of determine when you actually emit the results and computation of a window. So let's look through a concrete example. When you land on a Netflix homepage, you see a list of movies on the bottom, and we want to compute how many times somebody clicked on a certain movie box art. So it makes it easier to think about it in 4 questions, right? So what is it that you really want to compute? In this case, we're interested in computing the counts per movie ID. And where, that means, what's your timeline or time boundary and event time that you want to compute it over. And we're saying, every 4 minutes, I want to see how many people clicked on this certain movie. And I want to trigger the results every 2 minutes so I can see the progress of what's happening and make a dashboard out of it, right? And the last thing is, if I'm getting late events, how do I deal with it? So let's say I have a partner downstream, and I'm sending them the sum. And I say, okay, in the last 1 hour, I saw 100 clicks on this one. But because the mobile device was off, somebody's on the plane, they got off, and then we got an event really late. And if you cared about accuracy, you take that event and add it back and say, oh, sorry, it's not 100, it's actually 101 that you saw later on. So the last question kind of determines what do you do when you get late data, and how do you refine your results? So there's an important notion of watermarks. Now, we looked at grouping a window, but we could get events later, right? So how do we determine that a window is complete? We need some kind of notion of completeness. Even if you say we're going to add that event back later, there still needs to be some kind of notion of completeness. So watermarks are used for that. They usually lag behind the event time. And in an ideal situation, you'd be processing an event as soon as you see it in your system. And if you were to graph that, it would be like a straight diagonal line, as you see in here. But that's not really the case in practice. It varies. So here's an example. We have one stream where the events are in order, and we have the next stream on the bottom there where the events are happening out of order. On the one on the top, we say we are emitting these watermarks as the events are flowing through our system. And we say, okay, we've emitted watermark 20. That means we are sure that we are not going to receive anything after 20, and it's okay to do the computation up to the elements that included 20. And these numbers are timestamps, it's like a sequential timestamp. And on the bottom, when it's out of order, you can see that you get element 20 before you get 19, and your watermark says my window is going to be up to 17, right? So it gives you kind of a way to describe what the lateness is or completeness is about your system. So when you plot in practice this situation, you see that there's a skew between the ideal and when you actually generate the watermark. Because your watermark will always be lagging behind. There's a lag of getting that event when it generated into your system due to several network reasons or the device is offline. So when you actually look at the completeness of it, it's going to be skewed from the ideal line. And if you compute the watermarks too slow, then you'll be holding a lot more data in your memory before you flush it out and move on with your computation. If you're too fast, you will miss some events, and you'll have to deal with those events later. So it's not perfect. It's a heuristic watermark that you build out, and then you still have to worry about how to deal with delayed events. So working with late data in a real-time stream processing system, and if you want accuracy, it's one of the quite challenging things to do, especially when you're emitting results downstream. You don't know if the downstream sync is idempotent, what kind of side effects it's having. So it makes it challenging to build accurate systems when you have late arriving data. So everything I talked about has evolved over time. This is a great paper to read. It's evolved from systems like Millville, Flume Java, and many other older systems. And the terminology has evolved over time. And this paper gives a nice overview of how to not only have a programming model, but to reason about these things. And Apache Beam, which is incubating, is kind of a programming model, an abstraction, and they have a runner which you can target your generic APIs onto a certain engine like Spark or Flink. So let's quickly review what we looked at, right? We looked at how do we add time support, or what kind of time support do we need in terms of event time, ingestion time, and processing time. And windowing, we looked at watermarks. How do we deal with state and checkpointing? Checkpointing is really useful for recovering from failures. So every so often, the system could create a checkpoint, both for metadata about your system. So for example, if you're consuming from Kafka, then you need to remember your offset in your stream. And at the same time, you may be operating and creating counts. You also want to store those counts, and that's the data. So when you checkpoint both the metadata and the data, and you have a failure, you can recover from it and have exactly one's processing semantics. Okay, there we go. So in addition to those basic functionality, a lot of these frameworks also offer transformation functionality like map, filter, groups, joins, and it also allows you to specify a complex digraph of your job, and it takes care of computing it. And it also supports different events and sources and sinks, and some of them make it easier to even launch jobs by supporting some variation of SQL. It's generally called streaming SQL. Now, that's not all you need in an operating system to put it in production. You need a lot more than that. You need to make sure the system's stable and handles back pressure when there are choke points in your system, or a sink is getting slower, or your source is getting slower. Your system shouldn't keel over and die. It needs to handle the back pressure. You need a way to manage your job code that you're running and the life cycle of it. You may or may not have no downtime requirements. So you need to take all those into consideration. You need a multi-tenant environment. If you're running a lot of these jobs and the computation is varied, you want to maximize the resources. So you want to make it run in a multi-tenant environment. You need auto-scaling. You need dynamic rebalancing of workers. And you need a way to quickly push your code out into test and prod and run it against shadow data to see what's happening. So as important as the programming model is and the functionality a framework provides, it's equally important to pay attention to the operational features associated with that streaming engine, because that's what's going to decide how stable your system's going to be or not. So let's look at what runtime and execution engines we have at our disposal to deal with this problem. At a high level, if you were to do a back of the napkin design of it, you'd end up with something like this. You need something to buffer your events so that in the event of your producer going away, in the event of failures in your processing system, you have a way to get back to your data so you don't lose it. And you can use systems like Kafka, Kinesis, PubSub, you name a system that works for you. And then you have the execution runtime with all the operational features that we talked about and multi-tenancy. And then you have the execution engine itself that supports the notion of event time, windowing, and watermark, and things like that. And the other more important aspect of this is if you have a stateful job, you also need a good way of dealing with state. If it's a large state, how do you deal with it ideally? So what we found is if you have a system that supports local state that is backed off to remote state, that works the best because you're not constantly going over the network and looking up remote data. It's available locally when you need it, and when it fails, you can always recover it back from the backup store. How many of you are familiar with Kafka and how it works? Okay, quite a few. So I'm going to skip over what it does, but in one line, it lets you have a partitioned set of, it lets you partition your topic, and you can send events into those different partitions, and you can consume it as a queue, or if you have multiple groups, you can consume it as a pub subtopic. So let's look at SAMSA and how it works internally. So SAMSA has an interesting philosophy. This is related to point 9. They have a single-threaded model for actual processing, but for fetching the data, they have a multi-threaded approach. So for example, let's say you have 4 partitions that you're processing in one SAMSA job. It launches 4 threads, it prefetches the data, and it holds it in memory, so the processing is much faster. The processing itself happens on a single thread, and it goes through 3 steps. It goes through process, window, and commit. And during the window, you can set how often you want the window to trigger. So it's a pretty simple timer. Just think about it as you started a Java timer or something, and then it fired. So that's your trigger that we're talking about. So every 30 seconds, it's going to give you a callback, and you can decide what you want to do. And in your commit, it says, okay, I did the processing that you asked me to do. Now commit it. So in that situation, you could take a Kafka offset that you read from, and you could store it in a store. So that next time when you resume from a failure, you know which offset to start reading from. So commit lets you commit your position in the stream and gives you an opportunity to checkpoint your state as well. And that's both the local state as well as the metadata about where you are in the stream. So here we see that as the state changes, the local state, let's say, let's come back to our count click example. You're accumulating the counts for different movies. And it's stored in a local state, and it flushes that state to another Kafka topic, which it treats it as a changelog stream. So it's very much similar to the event sourcing pattern there, where every single change is emitted into a changelog stream. If you fail, it's going to read the whole changelog stream again. The problem with this is if you have really large state and you have a lot of updates on it, then your changelog stream is going to be really big and your recovery times are going to be very large. So we've seen that if you're upwards of 1 gig, 2 gig, it takes a while for it to recover from its cold state. And if you want to hook together a job graph in SAMSA, you actually have to connect them with topics in between. So you have to create the Kafka topics. You have to link them up for each job. So it doesn't take care of automatically running a complex digraph for you. You have to manually hook it up. So it looks very much like a Seta architecture there, and there's a lot more work you have to do. They are working on some enhancements to make this easier, but 0.9 didn't have it. So let's see what was missing out of SAMSA, right? So we didn't have any kind of event time support out of the box that it supported. There's no way to do any watermarking out of the box. You have to build all that functionality in it. And from a runtime perspective, it's kind of a single-threaded blocking model when it does I/O. So you could assign it one core in a multi-tenant environment if you're running in like a Docker or a Mesos-style environment. But again, when you're doing I/O, the resources are left unused. So they're changing this model slightly, and they're going to add support for multiple threads so they can leverage those resources better. So it's Spark streaming. How many familiar with Spark streaming? Okay, a few hands, good. So the idea behind Spark streaming is it takes the input stream and it actually chops it up into smaller batches. So it does micro batching. And batches below a second, below half a second have a lot more overhead. And we'll look at why that's the case in a second. So it chops it up into smaller pieces, and then it processes each piece. So it's not exactly like windowing. You may think it kind of looks like windowing, but it's just micro batching upfront. And what your results are also kind of results of those micro batches. So Spark uses a notion of RDD. So RDDs are, to say it briefly, they're a collection of elements that are distributed across a cluster, and they're partitioned. So every RDD can have multiple partitions, and you can do operations on it in parallel. And RDDs also, when you do transformations in RDDs, they also record the lineage of it, and the RDDs are immutable. So once you create an RDD and you apply transformations of it, you get new RDDs. And this lineage is captured so that when there's a failure, they know how to recompute it back because everything is mutable and they just applied functions over it. So it's the functional programming aspect of it that's leveraged quite a bit there to make it happen. So in this case, we see we have RDDs for each micro batch, and we have some operations on it. And then you could do some kind of windowing on it by grouping a couple of batches, but then it has to happen around the batch boundary, right? So if you say my micro batch is 1 second, then you can do your windows in multiples of those batch sizes. You cannot have an arbitrary window size. It has to match your batch size. So it's kind of a limitation. Spark 2.0, they have experimental support for event time. It's not fully out there yet, and it's not deployable in production, but you could take a look at the initial support they have for event time. But currently, they don't have it that you could use it in production. And Spark uses the notion of D-stream, which is nothing but chunked up RDDs, right? So the streaming is still micro-batched, and they just call it discretized stream or D-stream. So for efficiency, what happens here is if you see the 4 small rectangles in a bigger rectangle, these are all individual RDD partitions. And I've kind of overlaid 2 concepts here, so let me explain to make it easier. You could have, let's say you could have map and filter and flat map that you're, sorry, let's say you have map and flat map that you're doing it in your job. Spark can take a look at that and say, okay, map and flat map, I don't have to cross network boundaries to those operations. It's going to chain those operations together and launch it on one single JVM. And it's going to apply that to a certain partitions of RDD. So it can do that operation in parallel across all the partitions of an RDD that are spread across your whole cluster. So that's what it's doing here, like it's doing a map, a couple of maps, and then it's doing a radius by key at the end of it. Spark 2.0 has something called structured streaming. They just have more explicit data types, and they've unified how you do the API programming through data frames and data sets. And it looks more like SQL, so you can write one style of code, and you can apply it to both streaming and the batch side of the world. So they have a planner. It's very much like a database where they have a planner. It creates the logical plan, and at the end of the day, everything gets converted into RDD operations. So this is an abstraction that sits on top of RDDs to make it simpler for you to write jobs. And this just shows how the planner is incremental as well, and it needs to figure out how to match the micro-batching architecture as well. So when you actually deploy this in production, you have a few components in place. One, you have the cluster manager that you're launching this in. It could be something like Marathon or Meso, so that you can launch the driver program. The driver program kind of works like a coordinator. It's managing what's happening on the worker nodes and the tasks that it gets assigned. So if you have a job graph, it needs to determine which jobs need to go first and don't have a dependency. So it does kind of a breadth first scan, schedules those jobs in production. When they're done, it takes the results back, feeds it into the next set of jobs, and it schedules those jobs. Now with Spark, because it's micro-batching, every micro-batch, let's say you're doing 500 millisecond micro-batches. Every 500 milliseconds, the number of events it received, it's going to put it in a batch, and let's say you have 5 different operations you're doing on it, it's going to schedule that on the cluster. And every scheduling and every micro batch results in a new scheduling. So you're paying a little bit of overhead there, although it's pretty fast. But if you lower your micro batch size, you pay that overhead of scheduling every time. Now they do have what's called executor Java process that's running on all these hosts. So it's not a complete cold start. It does have the JVM up and running, but you're still making that scheduling call over the network and trying to get the job up and running. So we looked at with Spark. They currently don't have full back pressure support. What happens is every click or time click, so let's go back to the micro-batching example of half a second. So every half a second in its scheduling queue, it's going to schedule an event saying, okay, I want you to schedule this job onto the cluster. And regardless of what's happening to your processing and how slow it is, it's going to keep adding that event into the scheduling queue. So it's never going to stop. So as your scheduling delays build up, let's say you have a problem with your sync, or there's a node that's bad in the cloud and it's taking longer to compute. Then the back pressure builds up, your scheduling queue keeps growing forever, and eventually it'll run out of memory, right? And so we have this problem in production for some of the jobs we're running. So we have a monitoring job that looks at scheduling delays and kills the job and restarts the job, right? It's not ideal. So the back pressure support, we worked with the community to get the back pressure support in it. It's not fully there yet. There are, I think, a couple more JIRAs left to be completed there for the full back pressure support to get in. And the back pressure support is more like a PID. It's like a feedback loop from control systems. So it's not completely automatic. You still have to tweak a few knobs to make it happen. So Flink is another new stream processing engine. It's streaming at the core. Unlike Spark, it's not batch-based. It's actually true streaming-based. And it can handle both streaming, it can handle both bounded and unbounded data. So let's take an example here. So this would look pretty much similar to the APIs and functionality we have on the Spark side, right? You have all the same kind of operators available to do map and flat map and co-groups and updating state. And Flink also takes care of automatically managing the state that's associated with each operator. And it also takes care of checkpointing that state and creating backups of that state. So it creates a point-in-time snapshot of your data associated with each operator. and also what's happening to your input stream, and it stores all the metadata as well. So it actually offers exactly one's processing semantics out of the box. Spark does that as well, by the way, with RDDs and the lineage it holds on to. So we see here another example of how pipelining is happening, very similar to the Spark API we looked at. So they're pretty similar in that format. The way they get scheduled is kind of similar. Instead of having executors, you have something called task managers here. And instead of the driver program, you have something called a job manager, which coordinates what's happening on these nodes. They have a notion of task slots, which is similar to the tasks you saw in Spark Streaming. And this one shows the state that's being accumulated for each operator, which is stateful. So this goes into a little bit more into detail about how actually Flink does its checkpointing. And so you have the job manager. What happens is the job manager inserts barriers into the streams that are flowing, and these barriers actually don't block your processing that's happening on the different nodes. What it does is it lets the processing on that node align to the barriers, so that when barriers from two different streams, it'll wait for those to align. Once they align, it'll trigger a checkpoint. And these checkpoints, you can have a lot of checkpoints in flight because none of them actually block your processing, which is the best part. And when the two streams are aligned with the barriers, it creates a checkpoint and sends an ACK back to the job manager. The job manager records that checkpoint and also takes a snapshot of the state of the operator. So if the job were to fail at any point in time, it can exactly recover a point in time where you left off. So it does that out of the box. It has really nice support for something called save points, very similar to the database. So when your job's running, you can issue a command and say, create a save point for me. And then you can take that save point and either start a new code, provided it's compatible, or you can run another job starting off that state. So you can do a graph of very much like Git. You can take the state and then spawn off into different branches and run your processing through it. So either you could use it to do A/B testing, or you could launch a canary in prod and say, is my new job actually going to be able to successfully start off where this job leaves? And so you can do all that kind of testing without even touching your existing job that's running. So save points are pretty powerful in letting you do those kinds of things. So we talked about how do we do like analysis and real-time analytics on these streaming jobs and unbounded data. The one thing that I'd like you to kind of consider or question is, are there any applications that you write today and you have to write a lot of custom code for it, which could have fitted into a streaming model? And when we look harder, there are quite a few problems we look into where we could actually apply this model. So it's another, you could think of it as another pattern or an architecture to build your applications out of. So let's see what we are actually doing about this in our production. My team deals with three large areas. We have messaging as a service, which is where Kafka falls into place. We have stream processing as a service, and we have something called a management service that helps us manage our infrastructure across all these systems and automate the critical parts of it, so we can scale without having to scale people. And our philosophy is to create reusable functionality so people can quickly build their applications on top of us. So we might have libraries to do anomaly detection. We may have libraries to do some kind of specific processing that makes it easy to use for others. And we help curate these common functionality across different groups. So let's see what scale Netflix runs at. The background picture you see actually is a real store with that name in Berlin, which I was really surprised to see. So Netflix is available pretty much globally today, and it's the world's largest streaming network. And we have over 83 million subscribers enjoying our shows on 1,000 plus different kind of devices, and they're watching over 125 million hours of video every day. So they watched a portion of it while we're sitting here and watching this talk. So this leads to about a trillion events that gets processed in our pipeline every single day, and about 1.4 petabytes worth of data flows through it. We have peaks of 16 billion messages a second and 43 gigabytes a second data volume that's flowing through it. And we do all this with 4 nines of availability. So we have steadily grown the number of events we have seen in relation to the subscriber base that has grown, and we've had to evolve our system over time. We inherited an old system that we replaced earlier this year, which is what we'll dig into a little bit more deeper. So this is a snapshot of our management layer where the users can log in, and let's say they want to start generating events. So they create a new data stream, and what that does is it automatically provisions a new Kafka topic based on the ballpark guesstimate they provided us of what the traffic could be. And then they link up what the sync should be. They can declaratively specify what a filter is. It kind of looks like a JSON path filter. And when they say provision, we just provision for them. We launch it in a multi-tenant environment running on Docker containers, and they're up and running. So it's stream processing as a service, but the functionality is limited in what they can provide. And by default, they automatically get a dashboard for each stream they create, how fast the stream's doing, what are the syncs doing, are they healthy. We even have alerts based on if there are issues with lags. So you could have a bad XPath filter or JSON path filter that you specified, and it's taking too much of the CPU processing, and then you start falling behind because your source is producing a lot more data. And so we have alerts on that to notify that there's lags, and we can identify problems faster. So this is how it looks like currently. We have a set of fronting Kafka clusters, and the reason we've separated the fronting and the consumer Kafka clusters for isolation and availability. The fan out is pretty high for some of the topics, so if you were to leave it on the same cluster, it would impact our cluster availability. So we have something called Kafka Kong. We do this every week. We intentionally move traffic from one cluster to the other. We built this automation when we went live first, and due to a bug in Zookeeper and Kafka, we had an outage. And our larger clusters that were beyond 100 nodes didn't recover at all. So this lets us do a quick failover to a new cluster without losing much data. And we've done it several times in production since then. It's been a year, so we've done it at least 30, 40 times intentionally, and 1 or 2 times unintentionally. So this is how it looks like. We have events flowing through our pipeline. A fronting Kafka cluster goes down, okay, and we replace it. And it's fully automated. So this is how the event flows through. And we run it on Docker containers. We have our own runtime, and we use MySQL. We don't have any Mesos or Yarn. We just kept it simple. We're going to be moving into that. So what we're doing now in our next challenge is actually be able to allow users to specify custom code. And we are choosing Flink for it because of the reasons I mentioned earlier. Better state management, better tooling for reasoning about time. And we're going to look at Beam later. Right now, we want to make sure Flink's running in production and it's very scalable and stable. So we looked at the router use case. This is how it gets deployed onto our Titus runtime execution environment. There's a nice talk on QCon if you want to look at how our runtime is actually built. There's a separate team that builds this runtime, and we're going to move through this. Here's a job we deployed, and I'll show you an interesting part of it. Oops. I think it's stuck. Okay, so when we did performance metrics, we found that the Flink side of it saves us about 17% of cost compared to SAMZA, about 40% better CPU utilization, 20% better network utilization. So that's our initial numbers that we got for a specific use case, you may not be able to reproduce because your use case might be different, your deployment might be different, and you may not be running in the same cloud. Sorry for going over, but I'll be in the Netflix booth on the 3rd floor. So grab me if you have more questions, you want to chat more.